Hello. In this video, we're going to see a few other concepts of mass transfer. Let's see a few methods on how to measure KLa in a fermenter. Okay, so we've already seen the importance of KLa in the previous video, as well as what is KLa. So KL is your mass transfer coefficient, liquid mass transfer coefficient, that multiplied by the ratio of interfacial surface area to the volume of the fluid inside the fermenter is KLa. And primary importance of KLa is that it will give you an idea on how is oxygen transferred from the bubbles to the interface of the cells and to the inside of the cells. Okay, so there are a few empirical formulae for the measurement of KLa. A few empirical formulae are available for the measurement of KLa. But it's always very tedious to look for empirical equations and to calculate the value of KLa from empirical equations. We'll discuss that when we have the next class, or during the next class we'll discuss the various empirical formulae that are available. But for the time being, let's just say that there are a few empirical formulae or empirical equations available for the calculation of KLa. And it's very difficult to calculate from them. Therefore, what we can do is we can measure the value of KLa from the experiment or from fermenter directly. And what are the methods we can use for experimentally determine KLa is what we're going to see next. Okay, again, I've taken this topic from Bioprocess Engineering Principles by Pauline Doran. This topic is also available in the textbook by Schuller and Kagi. It's up to you whether you want to study from this or study from Schuller and Kagi. Right. Now, what are the points regarding measurement of KLa? First of all, it's very difficult to predict KLa in bioreactors during correlations. So this is the empirical correlations that I talked to you about. Mass transfer coefficients for oxygen can be determined experimentally. The measurement conditions of that in the fermenter, however, should match with those during the normal operation. So what we when you measure KLa, you might measure KLa with or without cells in them, or without the actual, or when you are performing or not performing the actual fermentation. So whatever fermentation process that you have in your mind, KLa measurement should be performed under the same fermentation conditions that you're planning to have your fermentation performed in. Therefore, measurement conditions should match those in fermenter during normal operation. What are the different methods here? You have oxygen balance method, you have dynamic method, and you have sulfite oxidation method. We'll see each of these in detail in the coming slides. Now, oxygen balance method is one of the widely used methods because of its simplicity and accuracy. The basis of oxygen balance method is based on the equation for gas-liquid mass transfer. So what you do here is, suppose you have a bioreactor. Okay, suppose you have a bioreactor with fluids in it. Okay, you let oxygen pass into the reactor. Okay, and then what you do is you measure what is the amount of oxygen that is passed into the reactor, and you would also measure the oxygen that comes out of the reactor, right? Measure the oxygen that is passed into the reactor, and measure the oxygen that comes out of the reactor. The difference in the input and the output, so input and the output, the difference between the input and the output will give you an idea on how much oxygen is transferred within the reactor. Okay, so that's the mass balance method you use there in order to find out how much oxygen is transferred into the reactor. So the experiment is very simple. You measure the oxygen content of gas streams flowing to and from the fermenter, and at steady state, the difference in oxygen flow between inlet and outlet is equal to rate of oxygen transfer from gas to liquid. So that's what I said. Input minus output will be equal to whatever oxygen is transferred from the gas to the liquid inside the fermenter. So we can put equations for that. The first equation is Na is equal to 1 by VL, this is VL here, 1 by VL Fg into CAGI minus Fg into CAG0 or CAGO. Okay, so Na is the rate of mass transfer. We've already seen that in the previous video. VL is the volume of the liquid inside the fermenter. F is the flow rate. Okay, F is the volumetric gas flow rate. CAG is the concentration of the gas, and I here denotes that variables or that conditions in the input region or whatever that goes into the reactor. Again, Fg stands for the volumetric gas flow rate. CAG is the concentration of the gas in in gas phase, or concentration of the component A, or especially oxygen here, in the gas phase at outlet, right? So this quantity divided by the volume of liquid in the fermenter would give you the value of oxygen that is transferred into the reactor. Now, in actual case or inside a fermenter, the concentration of oxygen is usually measured as partial pressure. So you can replace CAG here with partial pressure of oxygen, which is PAG, or partial pressure of oxygen in gas phase. Okay, so that's based on your universal gas equation, right? So you can have that equation where P is equal to CRT, right? You can use this equation and substitute for C in this equation with P by RT. That's what they've done here. So substitute C with PA by RT. R is a constant, a universal gas constant, whereas T, the temperature might vary at your inlet and the outlet region. So you kind of put T inside the bracket for I, or the input and the output. Okay, so I hope this is clear to you. The procedure is very simple. You measure the oxygen that goes into the reactor, measure the oxygen that comes out of the reactor. The difference between the input and the output oxygen concentrations will give you how much oxygen is transferred into the bulk liquid from the gas phase. Now, my question here are, what are some of the methods that can be used to measure dissolved oxygen concentration and oxygen solubility in fermenter? So this is one of the assignment questions for you. If you know the answer, well and good. If not, try to find the answer. I'll give you a minute to find the answer. Okay, I hope that should. What are the advantages of oxygen balance method? So I said it's one of the most reliable methods for measuring KLA. It also allows determination from a single point measurement, because uh, you can measure the oxygen concentrations at a single point, or all other, even if you want to measure the flow rate, okay, you, because that is also required, you can measure the flow rate, the temperature, the partial pressure conditions, etc. At the same point, right, for inlet as well as for outlet. So it allows a determination from a single point measurement, and this method can be applied to fermenters during normal operation. So if before you begin your run, or before you inoculate your fermenter with the microorganisms, you can use the same experimental setup in order for you to uh, uh, determine KLA value. Okay, so that's one advantage of oxygen balance method. You can use the same experimental setup to measure the KLA. You don't need a separate experimental setup to measure KLA. Using the normal operation before you inoculate, you can use that setup to measure KLA. So this method is also called a steady state method because you kind of measure the oxygen concentrations around during a steady state. Okay, so sometimes this method is called the steady state method. The next method that we have is called a dynamic method. We'll come to that equation that I've shown here towards the end later. Right, so dynamic method, as the name suggests, it's not a steady state method. We kind of have a dynamic kind of measurement there. So how exactly do we do that is what we're going to see next. So it's based on unsteady state mass balance for oxygen. And again, one of the advantages of this method is that the low cost of equipment needed. So here all you do is to measure the oxygen concentration, which you can simply do by means of dissolved oxygen probe. You have dissolved oxygen probe, DO probe. You can use this simply to measure the concentration of oxygen, and that's all you need to measure here. Okay, so you dip a dissolved oxygen probe into the reactor, you measure what's the oxygen concentration. Now, how do you perform this experiment is I've given some explanation here, but how do you perform this experiment can be explained by means of this diagram that is shown here. Okay, so what exactly do you do here is you let a run a rea le you let a reactor run. So you have a reactor here, inoculum there, or you have broth with microorganisms in it growing already. So what we do is we have in a normal reactor, we have a normal supply or a constant supply of oxygen into the reactor, and this oxygen is taken up by the microorganisms inside the reactor, right? Uh, what we are going to do is we're kind of going to measure how much oxygen is taken up by the microorganisms, and we're kind of going to have this curve generated, and based on this curve, we'll measure what is the value of KLa. Okay, so how do we do that is, I told you, you have a reactor with inoculum or cells already inoculated in it. You're kind of providing or sparging oxygen into the reactor. Okay, so let it run for some time after so you kind of get this part in the curve, right? Okay, because this here is a concentration of oxygen here in liquid phase, and the concentration of oxygen kind of becomes steady after some time after you inoculate, and when oxygen that is transferred into the liquid becomes equal to the oxygen that gets consumed by the microorganisms. Now what you do is let's say that at time t is equal to t0, this is where we begin our experiment. Okay, so in otherwise a reactor that runs normally, at time t is equal to t0, we stop the supply of oxygen into the reactor. So whatever oxygen was getting supplied into the reactor, we stop that. Okay, so we switch off the air or we switch off the oxygen supply. Now what happens here is when you switch off the oxygen supply, the concentration of oxygen inside the reactor will drop, right? So which is this curve here, that will drop immediately. Why? Because whatever oxygen that is already present in the liquid will now start getting consumed by the microorganisms. So you have a drop in the oxygen concentration. Now how long can you let this drop is, you have to be very careful here. You can switch off this device, or you can switch off the air supply until there comes a point that you are not going into the critical oxygen concentration. We've already seen or discussed this point on critical oxygen concentration. That's that point of oxygen concentration when the cells almost start to die, or that's at least the minimum concentration of oxygen required inside the reactor to maintain steady growth of cells. Otherwise the growth of cells will start becoming dependent on the oxygen concentration, because oxygen concentration will now become a limiting substrate, right? So oxygen will, we don't want that. We don't want the oxygen concentration to reach critical oxygen concentration. So what you do here is, uh, once you've switched it off and let it reach at this point, so this point you can fix it according to your requirement or whatever your experiment demands. And at this point, what you do is you kind of switch on the air. Okay, now at this point here, you switch on the air. So when you switch on the air, you're supplying air into the reactor, right? There is also simultaneous use of oxygen by the organisms, by the microorganisms. So it kind of takes time to, stabilize. So this concentration of oxygen will increase gradually, and then it takes some time for it to reach back to its normal concentration. So if CaL was the concentration initially, or was the concentration when there was an equilibrium, right? So at this point, or it takes some time to come back to this CaL, or the concentration of oxygen that was initially present in the reactor before you switched off your oxygen. Okay, now what you do here is you kind of measure the oxygen concentration or the dissolved oxygen concentration at various points when you go from the switching on point to the CaL. So you measure at different time points. You measure concentration of dissolved oxygen at different time points until you find no longer increase in the concentration of dissolved oxygen. So this is what you do when you perform the experiment in lab. You measure oxygen concentration at different time points until there is no longer an increase in the concentration of oxygen. And what you do is, once you get this plot, right, you get this plot, you can actually get this plot in your experiment. Once you get this plot, you can take 2 points here, right? You can take any 2 points here at, let's say, T1 and T2, and you get the values of CaL1 and CaL2 at any 2 points, and we're going to use a point CaL1 and CaL2 at T1 and T2 for your subsequent calculations. Okay, so that's what we're going to see next. Now, what happens in dynamic method is the rate of change in dissolved oxygen concentration during this period is equal to the rate of oxygen transfer from gas to liquid minus the rate of oxygen uptake by the cells. So like I said, you transfer oxygen into the reactor. It's not a steady state thing. You transfer oxygen into the reactor. So this is your oxygen transfer rate. This here, this term in this equation, KLA into C star AL minus EAL, is your oxygen transfer rate, minus the oxygen uptake rate by the cells, will give you the rate of transfer of oxygen into the liquid, right? So that's the rate of transfer of oxygen present inside the fermenter. Now, how do you go about the calculation of KLA from these data? At steady state, what happens is CAL is equal to C cap AL. So this we have already seen in the previous diagram. And also at steady state, what happens is dCl by dt is equal to 0, right? Your that's usually the rate of transfer is 0. There is it's under steady state. So dCAL by dt is equal to KLA into C star AL minus EL minus QOX is your initial equation. So now when this term becomes equal to 0, you have KLA into C star AL minus EAL is equal to QOX. And when you have steady state, you replace the CAL with CAL dash or CAL cap, right? And that's what is shown here. You have Qx is equal to KLA into C star AL minus CAL, right? So you replace, so you've already found what is the value of Qx from this equation. Okay, you substitute this value of Qx from this equation into this equation. Okay, so this equation dCAL, because actually it's not a steady state. We wanted a steady state. We assumed a steady state in order for you to find out the value of Qx. Once it's done, you substitute the value of Qx in this equation. So you have KLA into C star minus C minus KLA into C star minus C cap, right? So C star and C star will get cancelled. So you have C cap AL minus CAL for dCAL by dt. Okay, so if you notice this equation, what you can do is you can integrate this equation over the time points and the concentration, oxygen concentration points that we've already seen in the previous case, right? So we have like we took 2 points, CaL1 at T1 and Cl2 at T2. So if you can integrate this equation and assume constant KLA KLA is constant with time, you can integrate with respect to the boundary conditions. So what happens is you have CAL minus CAL cap minus CAL coming towards this direction and DT coming towards this direction. Okay, so you have 1 by CAL minus CAL, DCL by DT, or DCL is equal to KLA into DT. So once you integrate it, you get this equation, right? Over the time, or over the time period T1 to T2, from CAL1 to CAL2, the equation of KLA will now become ln CAL minus CAL1 divided by CAL cap minus CAL2, the whole divided by T2 minus T1. So it's just simple integration of this equation here over time period T1 and T2 at different oxygen concentrations, right? Now, this is a diagram here to show you that this equation has now become a straight line, right? So you can have this equation as y, you can write x, I mean, this equation now is y is equal to mx, right? So ln CAL, this term is equal to KLA into T2 minus T1. So if you plot ln of this equation, ln of this term against T2 minus T1, you should get a straight line with KLA, right? So that's what is shown here. You have a plot of ln CAL cap minus CL1 divided by CAL minus CL2 against T2 minus T1, which will give you a straight line with slope KLA. Okay, you measure CAL1, you can measure all other quantities during experiment. You can measure CAL cap, you can measure CAL1, you can measure CL2, you can measure T2, you can measure T1 during experiment, and substitute all this, try to plot a diagram, try to plot a curve. The slope of this curve will give you the value of KLA. Now, my next question here is, what are the limitations of dynamic method? You see, dynamic method is not free of any, or it's not entirely advantageous. There are a few limitations to dynamic method. You have to find out this answer. What are the limitations of dynamic method? And you can submit it along with your assignment. Take a minute to write down this question. Final method for dissolved oxygen concentration, or in order for you to measure KLA inside the reactor, is sulfite oxidation method. Again, this is used, but not as used as steady state or dynamic methods. What is the principle is, based on oxidation of sodium sulfite to sulfate in the presence of a catalyst such as copper 2 plus. Cupric ions are the catalyst there. You try to see how much oxygen is required to oxidize sodium sulfite to sulfate. So it's a pretty straightforward method here. But the problem with this method is that the results will appear to depend on operating conditions in an unknown way. So whatever KLA measurement that you get may be too high or too low based on the operating conditions you have. So it's this method is this method cannot give you a proper or a reliable KLA value. Therefore, sometimes you can also get higher KLA values. So due to these reasons, sulfite oxidation method is not that recommended. Okay, so